Hello, everyone. Lee Strange here from the Midwestern Archaeology Podcast. Today, I have the privilege of speaking with Dr. Brenda Hunda, an esteemed paleontologist whose passion for fossils has shaped a remarkable career in the field of invertebrate paleontology. Earning a Bachelor's of Science in Honors Paleontology at the University of Alberta, she shifted her focus from vertebrate to invertebrate paleontology, dedicating significant research to trilobites. Her passion for these ancient creatures led to a master's in geology where she focused on the middle and upper Ordovician trilobite biofacies and systematics. Later, Dr. Hunda moved to California to pursue a PhD in earth sciences at the University of California, Riverside, where her research centered on the stratophenetic patterns and ontogeny of flexicalamine, a type of trilobite from the upper Ordovician. Today, Dr. Hunda serves as the curator of invertebrate paleontology at the Cincinnati Museum Center, a position she's held since 2004. Her work encompasses a variety of roles, from curating the largest collection of upper Ordovician fossils in the world to developing educational programs and conducting vital community outreach. Her expertise also plays a key role in the museum's research initiatives and exhibitions, focusing on one of North America's most fossil-rich sea bottoms. Today, we are going to be discussing the geologic formation of America, what paleontological fieldwork looks like, Eastern America during the Ordovician, and much more. It is an honor to have Dr. Hunda here today to share her insights and experiences in the fascinating world of paleontology. Thank you very much for taking the time, Dr. Hunda.
Oh, Lee, this is great. My favorite subject is the Earth and life on it, so I couldn't be happier.
Firstly, how did you get involved in paleontology? What was the inspiration for this career?
Well, I think my mom would tell you that I've wanted to be a paleontologist since I could say the word, and that was probably about 3. So I was that kid that kind of went through the dinosaur phase and knew all the dinosaurs and loved fossils. I grew up in Saskatchewan in the 70s and 80s on small Air Force bases.
Okay.
So middle of nowhere, not a lot of museums around or anything like that. Actually, not a lot of fossil localities around at that point.
Okay.
And so I really gained my love from books, and I did a lot of reading. My dad used to call me a bookworm. And my love of the outdoors. So because there wasn't a whole lot to do on an Air Force base, you just go outside and play. And I just had this wonderful experience in my childhood of this freedom of discovery. Of course, within the confines of a secure armed base.
Right.
But when you're, 6 and 7 and you're allowed to just go out and come home for dinner, I think it really whetted my appetite for just nature and the earth. And for some reason, I just always was interested in what was in the ground. So I would take my mom's spoons and I would go and I would dig under the slide at the playground just to see how far down I could get and what was in there. And then my mom would get mad at me because I bent all her spoons. But not really mad, but So it's just ingrained in me. It's just something I've loved and I've never, ever wavered.
Did you ever have an experience where you came across a fossil or just a geologic feature while you were exploring that comes out from your early childhood or anything like that?
Yeah, not so much in Saskatchewan.
Oh, okay. I've heard that Alberta has better dinosaur fossils and such.
Saskatchewan does have some good fossils in the vertebrate realm, but, I wasn't in those spaces.
Right.
But and I also didn't really know what to look for. But once I got
you were a kid,
once I got to Alberta and got into my teenage years, there are fossil localities all over Edmonton, Alberta, of Cretaceous age. And so I would just go out and find, crocodile teeth, and little bones, maybe some hadrosaur teeth.
Wow.
And then as a teenager, I started getting involved in meeting people who liked fossils. They had a big fossil exhibition come to Cincinnati, and they needed volunteers. So at 16, I volunteered, and then I got to get to know people, and they would take me out in the field. And, we'd be pulling Edmontosaurus thigh bones out of the riverbeds from, the Saskatchewan River and fun things like that. So I really looked for those people that I could align myself with that had similar interests, and we would go out and have a great time. And then, of course, Drumheller is not too far away. So.
Oh, okay.
Yeah.
So was it your mom that encouraged you to seek out these opportunities, or was it just 15, 16-year-old Brenda wanting to... You knew that you liked dinosaurs and fossils, or not dinosaurs, but fossils, and you just pursued those opportunities.
Yeah. My mom was really great at giving me the courage and the strength to pursue my dreams. She was a single mom for most of my my older childhood and didn't have much time to facilitate me having these experiences. But she was always like, you go, you get what you need. Let me know how I can help. In fact, many of her friends would always say, Brenda is smart enough to be a doctor or a lawyer. What is this paleontology thing that she wants to do? She'll never get a job. And my mom would just be like, that's what she wants to do. That's what she loves. So that's what she's going to do. And I'm going to support that. So she was really instrumental in making me who I am and giving me the tools I needed to go and pursue these things myself. Me going out in the field and aligning myself with friends was me being probably a pain in the butt to the sides of a lot of people and asking them to help me to go out and experience things. And so, I think it was like, a twofold effort. Right?
That's awesome. That's awesome. Okay. I just out of curiosity, one last question on your childhood and brought you to paleontology. Did you have a first love when it comes to a species that you learned about that you just really loved? Or was it just a time period that really captured your imagination? What was your first fascination?
It was really funny because, growing up in Saskatchewan, Alberta at that time, dinosaurs were the big thing.
Oh, right? I'm sure.
So that was really what me. And I would get, go to bookstores and buy books that had very detailed information on dinosaur anatomy. And I'd memorize all the bones and the pieces of the bones and how they would go together on my own, just for fun and interest's sake. Interestingly, I went to undergraduate at the University of Alberta, which is a very good paleontology school. One of the only ones in North America that has an honors paleontology undergraduate degree where you specialize in paleontology. And I wanted to pursue vertebrate paleontology, but I really wanted to pursue mammals. Alberta is very good for Cretaceous, early Paleocene mammals and like multituberculates and all those fun things. And so I thought, well, mammals is where I'm going to be at. But the paleontologist who was the mammal paleontologist that I would have had to have done graduate work with didn't want women in the field.
Oh, wow.
Yeah. And he told me that he wouldn't take me as a student because I was female.
Oh, my gosh.
Yes. So we won't name names, but back...
Jeez. I mean, you can if you want to.
Yeah. Back then, it was not female rich as it is today.
Wow.
Where it's about 50-50 in terms of graduate students in departments being female. So I had to pivot. I couldn't leave because my mother had a car accident and I needed to stay and help take care of her at that time. And so I decided that I would go work on trilobites, which is really funny because the first 6 months of my master's degree, I hated them.
Really?
I was like, oh my God. Lee, the divide between vertebrate and invertebrate paleontology is a huge
so I've gathered
scale. So the divide between being a vertebrate paleontologist and an invertebrate paleontologist is like a Grand Canyon scale.
I'm sure. Yeah, I think
archaeology probably has the same divides, right?
Yeah, I would say if there was a big divide like that, it would be prehistoric and historic, or pre-contact and contact. But yes, absolutely.
It's always amazing to me how we tend to divide ourselves into smaller subdivisions. And so VPers and IPers are different types of people. And they often will also study, in different departments. IPers tend to be in geology departments. VPers, because they're more anatomy-based, tend to be in biology departments. So there's a real divide there. So for me, psychologically, having to switch from being a VPer to an IPer was a big... But once I learned about trilobites and I learned more and I got into I just fell in love with them and realized that many of the questions that I had were better served in the IP world because I could get more specimens, there's a greater sample size. I was interested in other things than what maybe the VP world could offer me, although I still love it all.
Yeah.
And so that's how I ended up focusing on trilobites.
That's so interesting. The invertebrate-vertebrate divide makes a lot of sense to me when you really think about it. So when it comes to data sets between those two divides, you just mentioned that vertebrate paleontologists tend to focus on anatomy and biology. As an invertebrate paleontologist, how do you glean information from the fossils that you find versus how you would if you were a vertebrate paleontologist? Yeah,
I think in my experience with invertebrate paleontology, we tend to focus a lot more on communities and ecosystems. It's not to say that VPers don't do that. There's a lot of great work. But when you are working on getting a 100-foot long sauropod out of the ground.
Yeah.
That, that is really kind of the focus. And you can collect some leaves and some insects and clams maybe to help you like figure out the environment. Whereas in invert paleo, especially in the Cincinnati, and your fossils are not in isolation from everything else. They are mixed in with
They're in
all
contact.
kinds of
Oh, okay.
other organisms.
Yeah.
You're really doing a community ecosystem kind of based study a lot.
That sounds fascinating, actually, because it's part of a greater context. That's a principle that's really important in archaeology as well. The artifacts are important and they're cool, but what archaeologists are really interested in is the greater context and what you can tease about the systems that are in place that brought those artifacts to where they are. And it kind of sounds like there's a similar principle there. So got another question. This is from my coworkers, Garrett, actually. He was curious about the field work that paleontologists do. There's oftentimes when people come in to ARI, they confuse archaeologists with paleontologists. I'm sure you've gotten that before, possibly. I mean, it seems more like people think archaeologists dig up dinosaurs and paleontologists dig up artifacts, but that's besides the point. Be that as it may, a lot of my colleagues, like I said, are curious about what fieldwork looks like. Can you explain the process of what it looks like to work in the field, and especially as an invertebrate paleontologist in this area, what that looks like?
Yeah, I think I would say as far as archaeology goes, and I did do some archaeology courses in my undergraduate.
Oh, cool.
Because we're sister studies.
Yeah.
A lot of the principles of how we tackle field work, the things that we need to know in advance before going in the field are similar, right? So the first thing, of course, for us is knowing the age of the rocks and what's going to be in them. And we use the same kind of stuff that you guys do, where we use maps to figure out, like, where's the best places to potentially get what we need. So we're looking for rocks of the right type, sedimentary rocks, and we're looking for rocks of the right age. So we have a good map from the geological history of life on our planet on what to expect, what, where. So I'm not going to go to Utah in the Mesozoic to find trilobites. So we know like where to target our efforts.
Okay.
Some of it is pure exploration, which is also a lot of fun, right?
Yeah, I'm
when
sure.
you just go to a place and you're like, I have no idea what to expect. I'm just going to go see. And that's fun. But for the most part, we have a good landscape and framework to work from. And then for us, really, it's about using maybe different tools. So oftentimes we're not a top-down approach where you guys kind of grid out the surface and work top-down. A lot of field localities don't have that viewpoint. We don't have that benefit of being able to have wide spans. That's not exclusively true, of course, of places that we can do that. But for the most part, we tend to be in outcrop mode. So we're looking at vertical walls of rock, typically, and or outcrops that kind of like, the hills are at an angle and you can kind of walk up. And then the tools are a little different, perhaps, right? So rather than as I say, digging in the dirt, which is what you guys would do, archaeologists would do. We use sledges and rock hammers, and sometimes I've even taken car jacks in the field with me.
Wow!
Yeah, classically, when you think about paleontology 100, 200 years ago, there was dynamite involved.
Oh my gosh! Same in archaeology too, actually.
Yeah. We don't do that anymore.
Schliemann, yeah.
So I think and then of course the record keeping is very much the same. We don't necessarily have a grid system. We do have datums, and we will, dig out according to that. This is mostly my experience in the IP world. Of course, dinosaur digs can be wide-ranging and vast over huge horizons. And so you can do sort of a similar grid-like system that they do in archaeology, and with a datum point, and you map everything as you go, except you're just dealing with rock.
Right. Well, I was about to say that makes a lot of sense, because in archaeology, the timescale is fundamentally so much shorter in time, or it's just closer to the present. So there hasn't been as much time to bury all of those layers, stratigraphy of history underneath, in the way that, something like an Ordovician fossil is really far. To do that top-down approach would take a lot of manpower and labor, and you may not even find anything. So that makes a lot of sense.
But I can tell you, I've been on archaeology digs with the museum and paleo digs, obviously my own and others. And when you're out there in the humid environment, sweating, it's 100 degrees outside, the hard work is the same.
Yeah, that's very true. That's very true.
It is still not easy.
That's very true.
Worth it, but not easy.
And it sounds like in this area, the Cincinnati area it's nice because it seems like the fossils are kind of there. It's a good spot for Ordovician fossils, but I know that's not true for all geologic time periods. And sometimes you have to go out in really remote areas. And it's just interesting because in archaeology, where you look for evidence of human settlements, oftentimes they lived in areas that are still okay and pleasant to be in today because humans wanted to live there.
Yeah.
Whereas you're talking about hundreds of millions of years ago where the climate of the earth was completely different. So
yeah, here in the Cincinnati region, the tri-state region, we are spoiled rotten. I think most people who grow up here think that being able to go into a creek bed and collect a rock with 7 different phyla of animals on them is sort of a typical thing to do, and that is really, really rare. I think we're probably the best sea bottom in North America. There's a couple of others I can think of that are good, but as far as diversity and abundance of fossils, I think Cincinnati takes the cake.
Wow.
And so there's been places in the world that I've been where I have hunted for fossils for 3 days and not found one.
Wow.
And then you find one and you're like, yay, a fossil. So being able to work in the Cincinnatian and all the information that's preserved here, that we have access to, even just staring at it, cutting the eye, is a real treat.
Since you pointed that out, I think you mentioned that in your presentation. Every time I go past it, I always pay attention to it, but it's hard to because I'm driving. So try not to. Yes, exactly. So it's right there. Have you ever gone up to it and poked around just to see?
I would love to, but the highway department says no.
Oh.
Right. So there are places you can go along the highways here in this area. And there are kind of places that are a bit more dangerous. The cut in the hill in the I-75 is a pretty dangerous place to have to go. It's close.
That makes a lot of sense. Yeah.
So we try to go on secondary roads.
Okay.
Rather than, the I-75. They frown upon that. My dream,
understandable,
however, is to rappel from the top down to the bottom so I can log the entire geologic section and collect fossils.
That would be amazing.
But I haven't gotten permission to do that yet.
I hope you do. I want to hear about it if you ever do. That sounds amazing.
And if I do it, I'm going to do it in like a jumpsuit with Cincinnati Museum Center written on the back.
Yes,
so everybody
some promotion.
driving by can see exactly.
That's amazing.
Maybe
That's
one
amazing.
day.
Yes, fingers crossed. So to just kind of switch gears a little bit and move to the Ordovician, which is your bread and butter, as it were. You've done a lot of research in this time period in Earth's history. Can you give us just a basic outline of what defines the Ordovician apart from the Cambrian period, the preceding period, the Cambrian period, and then the succeeding Silurian? So just kind of settle us in time about what's happening at Earth.
Yeah. So that's a big question.
It is a big question. I'm sorry.
No, it's good. It's a good question. It's a great question. There's a lot of things, so scientists divide up geologic time kind of based on major events and also changes in biota, fauna, and flora, major changes. So a lot of the time periods that we have demarcated are based on, say, like major extinction events. Hence, the one you might know, the end of the Cretaceous.
Yes.
Right.
Yeah.
And so there's a fundamental switch at that boundary between what was living before and kind of what was living after as a function of this major event. It's easy to find. It's easy to trace across the globe. Everybody knows it. We can divide time up that way. In the Ordovician, it's similar. The Cambrian is really known for more of the origination of most major phyla, major big classifications of life on the planet. Now, there are some that originated before the Cambrian, but you may have heard of the Cambrian explosion.
Yep.
This is the time that you start seeing life really exploding on the scene in complex forms. So body plans that we're familiar with today, like what it means to be an echinoderm, what it means to be a clam, what it means to be an arthropod, those are defined kind of by Cambrian time. But I like to think of the Cambrian as like a tree in winter. No leaves, no small branches, just the major branches in the history of life. So it's kind of bare, a little naked, but you got the big limb for the arthropods, you got the big limb for the mollusks, you got the big limb for the echinoderms. And then by the beginning of the Ordovician, we really see a shift in not originating major phyla, although there are some that do appear in the early Ordovician that way, but filling out the tree of life and what we call a diversification event. So this is the Great Ordovician biodiversification event, which begins at the beginning of the Ordovician. And it's taking that tree in winter and making it a tree in summer. So all the small branches grow, all the leaves come out and making it a huge tree of life. And so the body plans that we saw started in the Cambrian are really kind of, evolution just goes crazy on those body plans to the point where there's like a tripling of marine families in the ocean and a doubling of marine orders. From the beginning of the Ordovician up to about the middle into a little bit of the late. And so that tree is blossoming and we start to see the diversity, the biodiversity in the marine oceans that are comparable to what most of geologic time actually has. And so that diversification is really what helps to define Ordovician. The Ordovician is also a time of a lot more climate upheaval. At the end of the Ordovician, we have a major event, the late Ordovician extinction event, which marks that boundary between the Ordovician and the Silurian, where 86% of all marine species went extinct. It was a glacial event. So once again, we have that demarcation that separates it from the Silurian. So we have in the Ordovician a lot of cooling and warming trends that affect sort of diversity in the Ordovician, the mass extinction event. And by the time we get into the Silurian, it's really kind of a little bit more calm. It tends to be really a warmer period. There's not a lot of upheaval. There's some recovery from that extinction event, but most of the major players that we see in the Ordovician are still in the Silurian, most of the major groups, and it's just more of a calming time. The Silurian is really demarcated in geologic history by the first appearance of coral reefs.
Oh, okay.
Yeah, so we have reef and reef-like structures in the Ordovician, but when I'm talking about coral reefs in the Silurian, I'm talking about Great Barrier Reef coral reefs, not like a few little things here and there, what we would typically call a bioherm. So that is really sort of the beginning of the Silurian. And the Silurian is a huge transition time in Earth's history because we start seeing the first evidence of life on land, both in terms of plants and insects. And then by the end of the Silurian, we're seeing the first real like tetrapods starting to come on the scene.
Animals,
and so this is like a major transition time between life in the ocean in the Ordovician and life on land. And then by Devonian, we start seeing it like, go
take
crazy.
off. Yeah, absolutely. So just to be clear about timeline wise, the Ordovician is about how much time? And then I'm also curious about, once you're done with that, how long the ice ball planet conditions lasted for. I'm just really curious, and how a lot of the aquatic life survived during those conditions.
Yeah, so the Ordovician, I have to go back to my stratigraphic brain. It's probably about 50 million years in duration or so.
Okay.
And the mass extinction, global glaciation probably unfolded over the course of 2 to 5 million, I think.
Okay.
When we look at mass extinctions in Earth's history, geologically speaking, they look like a line on a stratigraphic chart, right? So they look like they're a blip, but most mass extinctions take millions of years to unfold. And so we're not talking about, there's dinosaurs one day and then the next day there's not.
Right.
We are talking about, actually, the Cretaceous dinosaur extinction was pretty rapid because it was an asteroid, relatively speaking. Yeah. But a lot of the big ones take 5, 7, sometimes even 10 million years for the whole thing to unfold and the consequences to be fully felt. So these are blips in the timeline of the geological history of the planet, but they're not small events.
Right. Yeah. Right. And because obviously life was almost fully aquatic during the Ordovician, was a lot of life just under the ice? Like were the oceans frozen over? What did it look like?
Yeah, so the glaciation in the end Ordovician wasn't a full extent in terms of covering the entire globe with ice, right? So ice does have to exist on continents. It can't grow on the oceans. So we do see a lot of evidence at that point in time of major ice sheets coming out of what's called Gondwana, which is a southern hemisphere continent that has Africa and South America and other continents on there as well. Really what you're seeing at the end Ordovician mass extinction and the global glaciation is sort of a contraction of latitudinal gradients. So when you think about latitudinal gradient, right, we think, oh, I'm going to go on vacation to the Caribbean because it's warmer at the equator than it is at the poles, right? So we know that there's hot at the equator, colder as you go up to the poles. That's the latitudinal gradient. And as the Earth cools down, basically the cold comes down towards the poles. So the warm sections of the Earth shrink and the cooler sections of the Earth expand. What that means is that anything that is really loving temperate ocean temperatures, maybe in, say, mid-latitudes, is now going to get cold. So they start to move down towards the warmer sections. So all life in the oceans is starting to contract towards the equatorial zones. That sets up some problems. That sets up a lot of competition. Because those temperatures are changing, animals that would have been adapted to one temperature regime and have to migrate maybe no longer maybe adapt it and go extinct. The other thing that's happening is as the glaciers are growing, sea level is dropping, right? Water has to come from somewhere. It comes from the oceans. And so sea level drops and all these wonderful, warm, shallow tropical oceans that are on the continents are being drained away. So all that habitat is disappearing, right? So it's a double whammy. It's a change in the temperature profile of the oceans latitudinally and how animals adapt to that. And also the seas basically are coming off the lands and shrinking and habitats being destructed. Now, what's fascinating is that the Ordovician is not a one and done extinction. Once the glaciers grow and they hang out for a while, eventually they have to leave, right? So everything that has adapted to these more cool environments in the ocean now have to get ready to heat back up again. Okay, so because glaciers are cyclical. And so everything that is now like, I'm cool with this, literally and figuratively, I'm cool with this. Now we're like, oh, it's getting hot. Those gradients are changing again. The warm part of the Earth is expanding. Now I have to migrate to follow those. Seas are reflooding on the continents as they do in the Silurian. That changes your habitat. And so there's a second pulse of extinction. So, yeah. So once you get global events like that, they really fundamentally change, everything about the oceans at that time.
When the Earth started to cool down significantly, I know that this is not always the case, but from what I understand, at least in the Pleistocene, which is the closest to humanity, which is why I know a little bit more about it than other times, but animals tend to get bulkier and bigger. Is that a trend you see during the Ordovician, like especially during this end time?
It's not a trend that we see. Actually, what we tend to see during this time is the appearance of what we call monospecific assemblages. So monospecific assemblages are basically one species that says, I can handle this, and they just bloom, like they just populate.
Take over.
Right, take over. So by the end of the Ordovician and the Silurian, most of the things that can't handle the changes are either out or gone. And the ones that can stick around, and they're like, oh, everything is empty. Let's party. The dance floor is open. And we're going to party. So then they just blossom. And so we start to see what are a lot of monospecific assemblages, where one taxa that is really adapted and can handle it now gets to reign supreme on the dance floor.
So before we say goodbye to the Ordovician, one last question. Cincinnati has some really good examples of Ordovician fossils. What were some of the dominant forms of life during the Ordovician, and what are some of the fossils that you have seen from this time period in this area?
Yeah. So the one great thing about the Great Ordovician Biodiversification Event is that it gave us a ton of stuff, right? So you can pick up a rock in Cincinnati that's maybe the size of your hand and find species in there from 7 different groups.
Wow.
There's echinoderms, there's brachiopods, there's bryozoans, there may be corals depending on where you're at. There's trilobites, there's sponges, there's snails. There's all kinds of amazing things. And so we're very lucky because we're on the receiving end of that massive evolutionary burst in the early and middle Ordovician. So the two groups that create the greatest biomass that we have in the Cincinnati are going to be the bryozoans, which is a phylum that is less known to most people. But if you find fossils that look like little trees, They're often confused with corals. Those are the bryozoans. They are absolutely everywhere. You can't miss them. They are a different kind of animal than corals, even though they kind of make an external structure to live in. And in fact, if you're interested in bryozoans, just Google them, because we have them in the modern. In fact, they're incredibly diverse. I
was about to ask if there were any examples modern day.
Yes, and they're different than what they were back in the Ordovician, but they are actually maybe perhaps almost as diverse, if not more diverse today than they were back then, which is rare. Wow. The second biomass of our oceans is going to be brachiopods. So these are the things, the shells, right? The land shells, as we call them. They tend to be things like Platystrophia and Raphinaskina. These are going to be everywhere. They're a major contributor. Once again, most people are familiar with shells. They look like clams. They're not clams. They're a different kind of group, but they have that appearance to them. But then out from those two big biomass contributors that probably made up most of what was living on the ocean floor, you have, large nautiloid cephalopods. These are related cousins, distant cousins to modern day squid that could get up to 20 feet long and were the largest predator in the ocean at the time.
Wow.
We have corals, which are very different from today's corals. None of the corals that we have back then are around. We have a different group of corals. We have the snails and lots of clams. People are familiar with those. The fun thing about snails and clams is they look like snails and clams.
You can point to it.
Million years ago, and they look like them today.
Yes.
Right? Not to say that there hasn't been a lot of evolution in between, but you can definitely recognize them. And other fun arthropods like sea scorpions, which are fun. So, gosh, so many cool things. And then there's all the really rare enigmatic things. The Cincinnatian is really good for weird echinoderms and weird jellyfish-like things. And it's also good for our City of Cincinnati fossil. We actually have an official fossil declared in 2002, which is an echinoderm, which I like to call an upside-down starfish on a dinner plate.
It kind of looked, from the pictures that I saw, it looks like it's kind of in an egg.
Yeah, so it's on it's like a disc-like thing that sits encrusted permanently on the back of something else. It could be a clam, it could be a brachiopod. Okay. They live there, they don't move, they grow. And so all the goodies on the bottom of a starfish have to be moved to the top of the starfish because the bottom is adhered to this other substrate. Wow. And so they're called egioasteroids. We don't have anything like them around today, which is why paleo is so fun.
Yeah, that's
see things
so
you're like,
cool.
what in the world is that? and we're world famous for them. And that's our official City of Cincinnati fossil, Isoropus cincinnatiensis.
That's the name.
Big mouthful.
Yes, it is.
Yes.
Is there anything that you are currently working on research-wise, or where your main curiosity lies in the Ordovician right now that you'd like to learn more about?
Yeah, so, there's always, despite 200 years of research in this area, there's still new things to discover. The micro world is really fascinating right now. So when we go out and collect, and people go collect, they pick up the big things. Right?
Yeah.
But you know that there's a whole other world under that. That's the small stuff, right? That you just gotta collect. They're not as easy to collect. You can't always see them very well, and then you have to do a lot of processing to get access to them. So right now I'm working on some ostracods with some colleagues from Hong Kong University.
Wow.
These are bivalved arthropods. So they're in the arthropod realm, which is my favorite phylum. They're very tiny, typically, and we don't know a whole ton about even some fundamentals about them, what species do we have in the Cincinnatian, and how are they distributed, and what are their environments like, and how are they making their living? We know basics. We've got some in the collection here at the museum that we can pinpoint to, but my colleagues in Hong Kong are really trying to figure it out. The other thing about ostracods, which are really fantastic, is their mineralogy. They're great for isotopes, and from isotopes you can get all kinds of things, like temperature proxies of the ocean at the time, so we can start to document, although this has been done with other organisms, start to try to document what the temperature was of the ocean in the Ordovician, and when do we start seeing those cooling trends we started talking about. So they're really great for geochemistry. So they're a lot of fun.
Yeah, absolutely. So when you say they're tiny, how tiny are we talking?
Microscopic.
Really? Yes. Okay, wow.
Now, ostracods are in the modern. They're everywhere, which is something I've also learned, because I never really thought about them before. They could possibly be in your bird bath at home.
Really?
They're
oh my goodness.
Fresh water, absolutely ever. And if you were to have a jar of them swimming around. They look like tiny little black dots.
Oh, okay. So it's visible to the eye?
It's visible to the eye, but hard to see in rock.
Okay.
There are some ostracods that do get big in the Ordovician that could be the size of maybe your pinky fingernail.
Oh, wow.
And those are huge. That's huge for these guys.
Yeah, that's the T-Rex of the ostracods.
Ostracods. That's right. That's right. That's like the
That's kind of cute, actually.
130-foot long sauropod of ostracods. Yeah.
That was amazing. So just to kind of switch subjects a little bit to the geology of North America. So it's obviously North America has been on a long journey. It's looked extremely different in the past than it does today. So using the greater Cincinnati area kind of as a reference point, can you take us through a journey that our continent has been through to get to its present state? And I know that that's also a big question as well. So just you can make as many generalizations as you need to.
Yeah, gloss over some details.
Yeah.
It's a long.
Yeah.
So of course, continents come together and they get pulled apart through plate tectonic action. And this has been happening since we've had continental crust on Earth, of which we have evidence of having that for over 4.2 billion years, right? So plate tectonics, the movement of the plates on Earth has changed configuration since almost the beginning, since there was a crust on our planet. So there's a lot of geology and coming together that makes the craton of our planet that is billions and billions of years old. So if you're like to dig down, far down as you want, we have rocks down there that form what we call the core or the craton of our planet, of our continent. And that took billions and billions of years to create, to evolve. So we've had mountain ranges down there that don't exist anymore, with spans of billions of years that have risen and have been completely weathered away. And we have massive rifts or cracks in the basement of our continent because of pieces coming together and splitting apart or failing to split apart, kind of like old scars that reactivate every once in a while. That's what the New Madrid fault zone is.
Wow.
And so there's that long history there. But starting really in the Paleozoic for the Cincinnatian, we underwent long period of what's called continental accretion. And continental accretion is basically where you start slabbing pieces of continent onto bigger pieces of continent, right? It's where you start building your continents. And evidence of continental accretion is going to be in our mountains. So we have two zones, right? We have the Rockies on the west and we have the Appalachians on the east. Those mountain ranges are the scars of continental accretion. So you can imagine taking those pieces away, like just take the Rockies and everything to the west of it off and take the Appalachians and everything to the east of it off. And that's really where we started kind of in the Ordovician. Starting in about 470 million years or so, we started seeing continental accretion happening on our eastern margin. So we would get what we call terrains or pieces of continental, smaller pieces that would come up and collide into the margin and attach with plate tectonics, right, and create mountains. And so that's really what the birth of the Appalachian Mountain Range was. The first of those being the Taconic orogeny, which happened at about 470 to 450 million years ago, which incidentally is where a lot of our fossils, a lot of our muds come from that vary the fossils that are in this region. And so there were 3 episodes of that. Okay, there was one in the Ordovician, one in the Devonian, which we call the Acadian orogeny, which basically put a lot of Pennsylvania, New York State, New England, and other parts to the eastern margin, and a lot of maritime Canada, and then a final collision during the making of Pangea, where we collided the eastern margin with what is present day Morocco, Africa.
Really?
Right, yes. So those 3 events are what gave us the Appalachian Mountain Range. It was a very tectonically active zone, kind of almost like what California is today to us, a lot of earthquakes. On the western margin, things were kind of quiet over there at this time, right? There was stuff happening, but not to the extent that we see on the eastern margin. The basement of the Rockies started being born at that point, but we started seeing a lot of those collisions. Those collisions really kind of warped the interior of the continent. So a lot of stress associated with that, right? And caused what we call the basin and bulge complex, where in front of the birth of the mountain range and the crushing stress from those tectonic activities, the continental crust down warped into a basin, kind of like a bowl, sort of where New York State is right now. And then in order to equalize that stress in our region, the tri-state region, a subsequent bulge happened. So that's what we call the Cincinnati Arch that we find in the Ohio, Indiana, Kentucky area.
That's so interesting. I wanted to ask about Eastern America being connected with modern day Morocco. So are the Atlas Mountains, would they have been at one point kind of part of the same mountain range as the Proto-Appalachian?
They are a different time.
Okay.
Yeah, they are a
Gotcha.
different time. But what's interesting is that if you go to the Devonian of Ohio and the Devonian of Morocco, of which I've been to both,
Wow.
you can find the same trilobite beasties on either side because
That's so cool.
they shared an ocean basin, right? So they were on opposite sides of the ocean. So although different species are there, the same types of trilobites are there. So studying in Morocco, Africa today seems like it's a world away.
Yeah.
Like, why would you go to Morocco to understand trilobite faunas in North America, in Ohio, and New York? And the answer is because rewind 350 million years ago, they were like opposite a small ocean basin and essentially neighbors tectonically.
Yeah.
Right. So paleontologists have to think not what things look like today, but what did things look like from a configuration back, and then piece that together. So it's fun to be able to do that.
Yeah, absolutely. Absolutely. And I know that for a good chunk of Earth's history, Cincinnati, tri-state area, and the Midwest was actually underwater.
Yes.
So what time period was that, and when did that end, I guess? When did we become terrestrial?
Yeah. So interestingly, most of North America's history is marine, and it's actually mostly in the Southern Hemisphere. So it's only been in the last 250 million years, excluding the fact that, seas have come in and gone off and come in and gone off, like we talked about the end Ordovician extinction into the Silurian, predominantly where it's become fully terrestrial and oceans no longer touch where we are, has been in about the last 250 million years of geologic time. And it's only been in the last 250 or so million years that most of the United States has been above the equator.
Yeah.
We've had times where North America has straddled the equator and bits and pieces, but really in the last 250 million years, can we really say like we are actually a Northern Hemisphere continent?
Right.
And only since the time of the dinosaurs, Cretaceous time, say about T-Rex, do geologists actually recognize North America as North America.
Oh, wow.
Like to the point where we can say this is it. It's become pretty formed and recognizable to what we have in the modern. Before that, we call it Laurentia, which is the time at which it really was, forming the eastern seaboard like we talked about. And then in the Mesozoic, the eastern seaboard becomes quiet. It's called the passive margin after the breakup of Pangaea. And then the west takes over and we start seeing the birth of the Rockies into the last 55 million years or so. So only when T-Rex is running around do we say, oh, now I see it. This is North America.
Oh, I see. And I know that at some point there was a large kind of like inland ocean.
Yeah.
So when was that? And I know that like it basically split North America kind of in two.
It did, yeah.
So yeah, tell us a little bit about that.
Yeah, that was the Cretaceous interior seaway. So if you go to places like Nebraska and Kansas and look for fossils, even in the dinosaur realm, well, these are not dinosaurs, but during that time, you will find tons of marine organisms, like marine reptiles. So Kansas and Nebraska and the center of the continent where the prairies are is famous during the Cretaceous for, pliosaurs, plesiosaurs, ichthyosaurs, large, huge fish like Siphaectinus.
Wow.
These are the big marine versions of the big reptile versions on land, right?
That's so cool.
And that is right in the middle of our continent. So that's part of the Cretaceous interior seaway. When there was a seaway that connected the Arctic Ocean, right, with all the way down through to what today is present-day Gulf of Mexico.
That is amazing. I'd really love to learn more about that time period because I've seen maps of it. It always blows me away that there was just an ocean right in the middle of our continent.
And we wouldn't know that without the fossils, right?
Yeah, exactly.
Tell us that. But this is the great thing about archaeology and also paleontology. It is the only time machine we actually have. But you can, just by studying the rocks or studying an archaeology site, like a village, you get transported immediately back in time. That's one of the things I love about it, right?
Yeah.
And you get to see things that are just weird, like not around today anymore, right?
Well, it really captures your imagination about like just the expanse of time and how strange and alien the planet must have felt like. Yeah. So I want to be mindful of time. We're getting close to an hour. I just have a few questions and then we'll wrap up. I know we really could. So I know the Pleistocene is not your forte, but I did just want to, because in your talk you mentioned, you talked a little bit about glaciers, and I just wanted to talk a little bit about that. And then also I just kind of wanted to ask you about invertebrate life during the Pleistocene, if there was anything of note that you wanted to bring attention to.
Yeah.
So regarding the glaciers, one of the defining features about the Pleistocene, which is quite a bit shorter of a time that we've been talking about, it's about like 1.5 to like 2 million years ago, I believe. One of the defining aspects was the presence of vast ice sheets that extended far south from the North Pole into what is now the United States. How did the vast glaciers of the Pleistocene affect the geology and topography of North America? I guess North America that was under the ice sheets, and if it had any effects on more southern lands.
Yeah, so I often joke, because I am Canadian, that this is how Canadians are going to take over America. We're going to do it with ice. It's going to take us about 2 million years.
Yes.
But the ice sheets, coming in and out of Canada, their main source, into this region, Kansas, Nebraska, kind of upper U.S., has happened in this area. We have evidence of 3 incursions and retreats. Right? So we know from the Pleistocene that there were about 20 cycles of glacial advance and retreat, and we have evidence this far south of 3, probably more. And the reason why we only have evidence of 3 really is because glaciers are huge bulldozers. So they scrape the land and they destroy evidence of previous glaciers as they go. And so when you think about going to Columbus, right? And you're like, wow, this is really flat up here. That's glaciers.
Wow.
They have scraped the topography from what it would have been previous to 2 million years into these landscapes. Down here in the Cincinnati area, of course, we were at the terminus of the glacier at about Sharonville. And so we get the benefit of having all the meltwater. So the glaciers would, start to melt back, and all that water has to go somewhere. And what it does is it takes all the sediment that glacier has bulldozed in front of it and entrained in the ice, and it dumps it, and it sorts it through rivers and streams and meltwater channels. And as that does it fundamentally changes the path of how water moves over the landscape. So before the glaciers, we had an ancient river called the Taze River system. This was the main way between 2 to 5 million years that we would get water out of this region. And things like the Mill Creek and the Great Miami would actually flow northward to hit this river system, and then it would travel out, ultimately cross Indiana and Illinois to the Mississippi to get out. But because glaciers are great bulldozers, they're also great ice dams. And as they come in, and they're like 1,000 feet thick, big walls, they prevent the water from using those channels. So new channels have to be carved. And through the advance and retreat of that 3 various times in the Cincinnati region, we got our beautiful carved valleys, our Mill Creek, our Great Miami, our Little Miami. The Norwood Lateral is a glacially carved valley that left a variety of deposits, including lake deposits when things got really slow and dammed up, to river deposits that create our great aggregate industry, and fundamentally created this section of the Ohio from Cincinnati, a little further east, all the way out to the Mississippi as a new drainage pattern to accommodate the fact that we had these big ice sheets sort of like in the way of this drainage. Now, of course, as glaciers retreat, they continue to dump all of these sediments behind them in a variety of landforms. So if you're driving up to IKEA and beyond, when you get to Union Center and you start to go up a big gradient, that's a terminal moraine. That's a big dump of glacial debris, sands and gravels that the last glacier ice sheet left us. And then if you drive to Columbus, you can see some sections have some beautiful rolling hills and all kinds. Those are likely glacial landforms that the glaciers left behind. And we can track all of those to help us understand like the rate and speed at which glaciers actually retreated and how they retreated. So ice sheets leave evidence of their advance and their retreat for us to like uncover.
Well, there was a map that you included in your talk of the age of the geology of the minerals that you find in the ground, and you can clearly see where the glaciers, like, they've left their mark. But I did have a question just on the topography of Ohio specifically. So before the glaciers, did that continental bulge that you described from the Appalachian Orogeny, was that still in place right before those glaciers just kind of flattened out the Midwest? And if so, is that what gives us kind of like that really awesome sneak peek into the earth of, like, I think you described it as a muffin top.
Yes.
Did it cut the muffin top to give us kind of like the view of what's below us?
Yeah. So I think a lot of people do ascribe the glaciers to cutting the to eroding that muffin top off. But they're not long enough or powerful enough to do that. So really what happens is that tectonic activity that we talked about, where we were experiencing that compression on the East Coast and causing that bulge, that bulge is still with us. That's
Really?
a tectonically permanent situation
Wow.
in the crust. And you can see it if you map it over the tri-state region. So it's not something that you can go up to a crop and say, oh, I see the bulge.
Right.
This is a large geological multi-state feature. But remember we talked about how after 250 million years, we basically became land?
Yeah.
Right. That's a huge part of the story. So once you become land, it's very hard to make new rock. It's not really a great place to make rock. You can make rock in lakes and streams and stuff like that. But for the most part, it's an erosive environment. And we know this, right? Ohio River gets muddy in the spring. All the tributaries and watershed dump sediment in there. And then that sediment is transported down to the Mississippi where it's dumped in the Gulf of Mexico. Okay, so oceans are where really great rock is made. Land is not where great rock is made. So all the rock that we had just built up over the last 500 million years or so in the geologic column has about 250 million years to erode down.
Wow.
And so that exposure to just erosion, wind, rain, snow, ice, whatever it may be, took about 250 million years to take down. The glaciers are kind of like a small piece of that. Certainly they have carved a little bit as they've come through, but not to the scale at which we're talking about. And in fact, if you think about Cincinnati and take the valleys, the Little Miami, Mill Creek, and the Little Miami, and you take those and you fill them back up again, like pretend that they're full to the top, that horizon that you see when you look out over the landscape that connects Price Hill with Clifton, that would have been the original level of the hills.
Really? Okay.
Prior to the Taze River system coming through.
Gotcha.
So all the erosion from the Taze and the glaciers in the last 2 to 5 million years or so, which is fairly young, is what creates our valleys and streams today.
Okay. So from what I'm understanding about what you're saying is that this bulge, this muffin top that was created from the orogeny is so fundamentally a part of this continental crust that we're in Eastern America that the glaciers would have had to been way bigger to really make that kind of cut. Yeah, which there's just not enough time to explain all of that. Okay, gotcha.
Yeah. So the glaciers, have been around for us at about down in this region for about 2 million years or so back and forth.
Yeah.
They just don't have the extent or the amount of time it takes to get rid of them.
Gotcha. Okay.
They played a role, but they weren't.
It wasn't the only thing.
It wasn't the big fish in the pond.
So during the Pleistocene, a lot of the attention gets put on the megafauna vertebrates.
Yes.
For good reason. They're super interesting. They're not around anymore. But what did the invertebrate life look like during the Pleistocene, if it looked significantly different at all? And then also, how was that life affected by the late Pleistocene extinction event, which I know wasn't a mass extinction event in the Big Five. The Big Five, yeah, but it was still significant enough to affect speciation and stuff like that.
Sure, absolutely. Yeah, this is a great question because I'm as fascinated by the big guys as you are, right? I mean, it's easy to be fascinated by giant bison and mammoths and mastodons and
camels.
Giant ground sloth.
Oh my goodness. So cool.
What is that? Right? That's weird.
Yes.
And fascinating. So I totally get that. But remember, we're talking about an ecosystem, right? So while those get to play, like T-Rex gets to play in the dino world, there's a lot of other things that have to support those large animals, and ecosystems are fundamentally shifting at this time. So it's interesting to see not just the invertebrates, but also the small mammals and birds and other things that are around. So you could go to the Pleistocene and other than a few very large weird things, probably recognize most of everything else. So there's rabbits, there's turtles, there's ducks, there's clams, there's insects flying around. Many of the same creatures that raccoons, possums, just all the kind of things that you might expect in an environment that we see today still existed in the Pleistocene. Different species, some of them the same actually. raccoons never seem to go away. They're just
Wow.
able to do everything, including living in highly urbanized environments.
Right.
They're just like the perfect adapters to everything, which is why I give credit to them, even though people are annoyed by them.
Shout out to raccoons.
From an evolutionary perspective, they're awesome. But so all those guys are there. Fish, everything is in there.
Looks very familiar.
Looks very familiar. With the invertebrates, really, there is going to be extinction involved in that as well, because temperature and all of that affects that. But the documentation of those extinctions probably aren't as awesome or as great as what you would see. So I did a little digging in the research because I was like, I need to know like what is going on in the invertebrate realm of Pleistocene. And, there's extinctions kind of species by species in every group. I know that there's the dung beetle gets extinct in Australia, for instance.
Interesting.
That was an interesting little fact. One species. Bivalves get hit, but none of it is crucially hard enough to decimate faunas or anything like that. It's just species here, species there that may not adapt to the changing climate as well.
It seems like the species that got hit the hardest were the ones that were the most adapted to take advantage of the colder environments. Yeah. Just seems like maybe the invertebrates were more, you can correct me if I'm wrong, were better placed to not suffer as much. Yeah. They're a little bit more adaptable when it comes to fluctuations like that.
Yeah, and there seems to be, from what we know about extinction of the Pleistocene, kind of a size barrier.
Yeah,
right? So
yeah.
certain animals of a certain size, whether they be birds, because there are some big birds back there. Or mammals tend to get hit harder as a result of the changing climates. Whereas if you're a little clam living in the bottom of a river system, you're probably pretty okay. A lot of marine faunas that we talked about before might have some extinctions related to changes in the latitudinal gradients that we're seeing and cooling ocean temperatures. But the ocean's a pretty good buffer usually. This is not going to be as hard a hit.
And it would be harder for any humans to get their hands on a bivalve at the bottom of the ocean. Whereas if you're a large lumbering mammoth, tasty, and it feeds you for a long time. So that makes a lot of sense. Because I know that humans, it's debated how much they played a part in the late Pleistocene extinctions, but they definitely played at least some part.
I'm waiting for everyone to figure it out.
Yeah, I know.
It's not my deal, although I'm fascinated by it, of course, because I love everything to do with the Earth. But I think obviously we've come to a point where we know that it's a climate human.
Double whammy. Yeah.
Good, because it has to be a double whammy in the sense that it's almost on every continent on Earth. This has got to be a bigger story. I think that we've come to that. It's just what are the factors, the interplay, and maybe the percentages of how that double whammy came to be.
I looked at a map of where the extinctions happened the most. And then what's kind of interesting is that it seems like it was the worst where humans were entering the environment for the first time, which from what I understand about paleontology and just like ecology in general, if you have, I guess, a new creature that's well adapted to this new environment that they haven't been a part of yet, they decimate. The species around them aren't used to them. They're not adapted to this new apex predator that comes and is
right, exactly. And we see that throughout Earth's history in the marine realm. We think about invasive species as being bad things today. Most of it being human mediated in some cases, but invasion of species into new environments has happened throughout the entire geologic record. This climate is constantly changing. Yeah. And so as we go into, this new climate warming that we're experiencing, we're going to be seeing a lot more of these migrations of animals into their preferred environmental environments. Their preferred environmental tolerances, right? They're going where they think they can do best, but that means that they're entering environments where they haven't been before. Yeah. And some very sensitive environments, like, the environments at the bottom of the ocean around Antarctica are now being invaded by very large spider crabs that are decimating, communities down there that never had a predator like that. Yeah. And so this is a common narrative throughout Earth's history.
Yeah, absolutely.
Not to say
makes
that
a lot
we're
of
not
sense.
Responsible for some of it now,
right?
But it's not unique.
It's a pattern that we can recognize in other times in Earth's history. Yeah, so that's what I have for the Pleistocene. I guess just as a final wrap-up question, is there anything that archaeologists, from your perspective, can learn from paleontology or vice versa that you've noticed about the approach that archaeologists have?
I think my big takeaway from having experienced a little of both.
Yeah.
A lot of one, a little of the other.
Yeah.
Is not that so much that we can constantly learn from each other. There's not one thing, I think, but more that we should be learning from each other.
Yeah.
We are, the way that we do our methodologies, the way that we do our science, and the way that we think about approaching, say, field work or approaching history or prehistory is really the same. It's just a different time frame. Now, I'm going to divorce human culture a little bit from that.
Sure.
Trilobites didn't have culture as far as we are aware of. So that is an element that makes humans unique amongst the animal and plant kingdom, and that we don't have much to bear on that.
Yeah.
But the way that we move and live in the world, the resources that we use, the ecosystems that we occupy as humans and another species on this planet back then are much the same way, that we think about in terms of ecosystems and, resource utilization and things like that. And so while we humans are unique in that sense and come from a different tactic, thinking about how we use and engage in our ecosystems and what those ecosystems mean for resources is something that we can both benefit, I think, from exploring more.
That's a great answer.
I just think that we use different tools and different techniques, and maybe our time frames are different.
Yeah.
But we're really going at it about just thinking about wow, what did the past look like? And what were organisms on this planet doing? Be it human or trilobite or dinosaur. And from that sense, we ask a lot of the same questions.
Yeah. Absolutely. Well, Dr. Hunda, thank you so much for your time. It was a fascinating interview. Appreciate it a lot.
I loved it. And anytime you want to talk about the Earth or life on it, human or otherwise, let me know.
Absolutely. Well, thank you so much.